There you go, you're good to go.
At that point, life expectancy starts going up, right?
All right, why don't we start? I would like to welcome everyone for our War on Lecture series. We have a very interesting topic today, recent innovations in concrete materials and technologies. And our speaker is Professor Jan Olek from Purdue University, where he is the James H. and Carl H. Cure Professor of Civil Engineering. Jan also serves as the director of the North Central Superpave Center and is also the director of the Pankov Materials Laboratory. He received the master's degrees in construction materials from Krakow University in Technology in Poland, and also from in materials and structures from University of Texas at Austin. And then he received his PhD in cementitious materials from Purdue. He held academic appointments at Colorado School of Mines and Penn State University, where he was my professor who taught me concrete. And thank you very much for that, Jan. Then he returned to Purdue in 1994 and accomplished many things. We don't have time to go through all of his awards and paper publications, but all I can tell you is that his current research interests include sustainability of concrete materials and structures, durability of concrete and asphalt pavements, and applications of 3D printing technology for structural optimization of cement-based materials. And today he will cover some of those topics, in particular discussing binding of CO2, very important problem, and manufacturing, additive manufacturing, 3D printing of concrete. So with this, please welcome Professor Jan Olek.
Thank you very much, the department and Mikhail, for the invitation. I'm honored to be here. And what I would like to do is to share with you a couple of topics I'm working on. The innovations in concrete seems like not a very exciting topic maybe, because a lot of people who are actually not working in concrete, they say, what is there to innovate in concrete, right? We use concrete for hundreds of years, and it seems like there is really not that much of exciting things that happens. But I would like to think that I will be able to change some of your thinking, maybe, if you're thinking along those lines. And what I would like to start with is a brief summary of the paper that I wrote with about 15 colleagues. Professor Bernacki from Tennessee Tech was the leading author on that. That paper was commissioned by the Journal of American Ceramic Society. And what they were interested in is our take on 21st century cements and construction technologies. And we started by looking somewhat at the history of cement. You know, the patent for Portland cement was issued in 1824. And for about the first 80 years, there was quite a bit of innovation in the cements that became available at the beginning of the 20th century, 1900s. They were very different than the cement that was patented. But then the innovation kind of stopped. So over the next 100 years, there were only incremental changes in the chemistry. What was happening is, there were competing pressures of constructability and cost, and those were mostly addressed by use of admixtures. So I would say from 1900 to about 2000, there were progressively new admixtures have been introduced, and they solve actually a lot of constructability problems, allowed for production of cements that will incorporate waste materials, improve the properties, and so forth. But we kind of reached the limit on that, and now we have driving forces that are pushing toward other directions. Automated construction, more sustainable cementitious materials are the things that are currently on the top of the research agendas of many people working in this area. So when we were preparing this paper, we were looking at the key scientific pathways for development of new cementing agents, new cementing binders, and new construction solutions. And we identified several of them, as you can see, and those were driving some of those construction technologies. But what I want to focus on are the two circled here, additive manufacturing and alternative binders. And they are linked very closely to issue of resource availability, both of them actually, climate change and construction technology. So I will start by discussing very briefly how we make cement, because I imagine that not everybody here knows. If you do, apologies, but there will be a summary. So we start with raw materials. As you can see, limestone is one of the core materials. We have clay and shales. They are sources of silica and alumina. Limestone is a source of calcium oxide or lime. We have iron oxide, silica sand. And we powder them and put them into the kiln that needs to be fired up to about 1450 degrees Celsius. That's the hot end of the kiln. That's where the clinker is being made. In the process of making the clinker, one of the first steps is decomposition of calcium carbonate or limestone. As you can see, we get lime that is becoming a vital component of calcium silicate type of the binder, which the Portland cement is, and we are emitting CO2. The final product contains about 70% of those calcium silicates. We use the abbreviations to identify what they are, but this has 3 molecules of calcium and 1 molecule of silicon dioxide, so it's tricalcium silicate. And then there's a dicalcium silicate. It has many polymorphs, but the beta form is the one that actually is reactive with water. So both C3S and C2S, beta C2S, are hydraulic. They react with water. And then there's about 20% of tricalcium aluminate and C4AF combined, and 10% other materials. But anyway, those two compounds we'll be looking at in terms of sustainability and what can we potentially change in making the binders more sustainable. If you look at the energy balance and associated CO2 footprint, you will see that about 40% of energy that is associated with the manufacturing of Portland cement is associated with generating this high temperature, fuel burning. And we have about 50% comes from decalcination of calcium carbonate or limestone, and 10% distribution costs and others, right? When we make cement, what do we do with it? And we have this great powder. The primary components, about 70% combined, dicalcium and tricalcium silicate. We add water, they are hydraulic, and they hydrate, form something we call calcium silica hydrate. And as a byproduct, they also produce calcium hydroxide. Concrete is the second most largely consumed materials on Earth after water. There were 4.2 billion metric tons of cement that were produced in 2018. In the world, in the US, about 88.5 million. US actually is not a very large producer of cement, comparatively speaking. China and India are by far orders of magnitude larger producers, and that's associated with population and urbanization rates that are present in those countries. And you can see that the production of cement tracks the urbanization rate very closely. When people need to live somewhere, they need the highways, they need the bridges, and so forth. But the issue of that is that when we add the balance of CO2 production, 1 ton of Portland cement results in about 0.9 to 1.2 tons of CO2. Depends what method and what type of cement we produce. It's variability, but if you remember 1 ton of cement, 1 ton of CO2, if you look at 40 billions, that would produce a lot of CO2. So the cement industry is responsible for about 5 to 8% of global man-made CO2 emission. Cars make more CO2 than cement does, but cement industry became a target of very concentrated efforts to reduce the CO2 associated with the production of clinker. There's also issue of natural resources, right? We need to mine a lot of limestone and other materials to produce the cement. So cement industry took notice of the fact that they had been targeted for doing something, and they did a lot of things. They increased the efficiency of the kilns. They produced more recycling of heat, or they implemented more recycling of heat, using the hot gases to pre-calcine, reduce the energy, and so forth. But I think we reached the limit of what can be done in terms of cement production. So the cement industry actually started looking at alternative ways of producing binders. And that's what I will be talking about right now. So to give you an idea what is involved here is, this is a phase diagram that has the three basic oxides that are present in cement: calcium oxide, silicon dioxide, and aluminum dioxide. And you can see that as we go toward the corner here, which has a lot of calcium oxide, we increase the hydraulic reactivity. So the Portland cement, ordinary Portland cement, is located here, has a lot of calcium, has a silica, and a little bit of alumina. And the C3S and C2S are the main components of Portland cement. But there are other compounds here, like rankinite or wollastonite, that are also in the region, but because they are far away from CO2 location here, they are not hydraulic. Right? So you can mix them with water, nothing will happen. But if you think about it, if I could make a cement that will have 1-to-1 ratio of calcium to silica, I wouldn't have to have so much limestone like I need here, because I need 3 moles of calcium per 1 mole of silica. Yeah, it's not going to be hydraulic, but I will need less limestone, so conservation of natural resources. And it turns out that you can actually make cement that contains those 2 non-hydraulic compounds at about 250 degrees lower temperature than you need for production of clinker that is associated with ordinary Portland cement. So instead of going to 1450 degrees, you can make it at 1250. You think maybe 250 degrees is not much, but it actually is a lot of energy. If you multiply it by the billions of tons that we are making, that actually is a big saving. So to summarize, we have high lime content in ordinary Portland cement that's associated with higher emission during the calcination process, higher emission of CO2 during the calcination process. We need high production temperature. However, if we want a lower CO2 footprint, we need to go the other way. We need to go away from the CO2 corner there. So that's how we arrive at the topic I want to talk about today, which is CO2 activated binders. So hopefully you remember that when we were making B-lite and E-lite, or C3S and C2S, we produce a lot of calcium, or a lot of carbon dioxide, CO2, right? So what if we took that CO2 and actually use it for making a binder? It turns out that those non-hydraulic materials can harden when exposed to CO2. So you can almost have like a closed cycle, all right? So let's see how that all shapes up. The first paper that pointed out to that possibility was actually published by the 2 professors from the University of Illinois in 1978. They said that the ability of non-hydraulic calcium silicates to react at high concentration of CO2 opens new area of potential cementitious materials. But they also say, so there's a copy of the paper, they also said that carbonate cements that harden due to the exposure to CO2 are a long way off from commercial use. And they were a long time off until about 2008, That's where a private company called Solidea Technologies, a startup, came to Purdue with the proposal that we should start looking at potential of producing cement with lower CO2 footprint. They actually had a patented composition of that. And the beauty of the product that they were pitching at the time was that you make it from the same components that you make regular Portland cement. You use the same kiln that you use for production of regular Portland cement. You just need to fire it up to about 1250 or 1200, so about 250 C lower, and you don't produce so much CO2. And since you are making either CS, 1-to-1 calcium to silica ratio, or C2S2, like rankinite, you need actually less limestone. So we worked with them for the last 10 years, and last January, that company was actually purchased by largest cement producing company, LafargeHolcim. Holcim used to be Holcim is a Swiss company. Lafarge used to be a French company, very big producer of cement all over the world. Holcim actually bought Lafarge, and they became this huge conglomerate, LafargeHolcim. Lafarge used to have their own efforts into making a low CO2 materials, but they abandoned it because the product that was offered by Solidea Technologies was actually better and more economical. So right now, they converted 2 cement plants into producing that, one in Europe, one in the US. The biggest bottleneck right now is specifications, right? Because the performance of that material is not known. It's only about 10 years old, and there is no specification for the implementation. So there's very diligent effort right now, people working at many institutions to address certain issues that will have to be addressed before the specifications could be created, both for testing of the materials, but also for designing using these materials. So we need to know what properties those materials are having. So what we were looking at is performing some sort of a fundamental comprehensive study on the effects of carbonation on the calcium silicates and the reaction products in order to understand the mechanism, how to improve the process of carbonation itself, and to determine what are the mechanical properties and so forth. So what I will do is briefly take you through the methodology that we use for addressing some of those things. So we look at multi-levels scale-wise, starting from nano levels all the way to concrete. So I will just highlight a couple of things. Don't have time, and frankly, that's maybe a discussion for people who are really into it, but hopefully that you'll find it interesting to see how you can go about putting together sort of a comprehensive picture of how material can potentially behave and try to model the behavior, because not everything could be tested, and we need to rely on some of the modeling in order to be able to maybe predict performance. So what we've done, as in one of the studies, we synthesized the components we wanted to work with. So we synthesized C3S, we synthesized 2 forms of C2S. I told you before that beta is the one that is reactive. It's actually part of the regular cement. But if you don't cool the clinker properly, you are in danger of producing gamma polymorph of that. That's totally non-reactive. And then rankinite and wollastonite are the components that are part of this industrial-grade calcium silica cement that is produced by Solidea and Lafarge at this point. So carbonation process is a process that happens to every concrete. In fact, concrete carbonates naturally. There is a lot of calcium hydroxide as a byproduct of cement hydration. That calcium hydroxide will carbonate. And over time, there is a danger that if the carbonation depth is too deep, or if the concrete carbonated to the level of steel, you will have a problem with corrosion of reinforcement because the steel doesn't corrode in concrete because it's being passivated by a highly alkaline environment of the pore solution that surrounds the steel rebar. But the carbonation actually leaches out calcium hydroxide, and that's one of the process. Leaching of calcium creates the SiO2 or silica gel, and pH drops and rebars will start corroding. CO2 from the atmosphere comes in and creates the carbonate ions. And carbonate ions react with the previously leached Ca and form calcium carbonate. So the circle kind of closes. We decompose limestone, calcium carbonate to make the cement, and over time we are going back to making artificial limestone. So that gives you an idea that the concrete can actually be a sink, if you will, for CO2, right? You can bind it. That's for regular concrete or regular cement. But if you have different calcium silicates with the different ratios of calcium to silica, it's the same process. So non-reactive components of the cement that I was mentioning, they can carbonate the same way. And when you carbonate, you will see the phases that form. So you can see CCs as a calcium carbonate. That's a main binding medium. So rather than calcium silica hydrate, which is a main binding medium in regular Portland cement, we have carbonate or artificial limestone that binds everything together. This is the unreacted cement grain. This is the silica gel. You can see it forms on the outer surfaces of the original cement grain, and you have some porosity. If you look at a little bit more detailed scale, you will see that the silica gel actually forms a very tight layer around the unreacted grain. And there is also, this is the main binding phase, calcium carbonate. It turns out that the silica gel is not a pure silica gel. We call it calcium-modified silica gel. It actually has some calcium, and the amount of calcium that is present in the gel will actually determine the mechanical response and chemical response of the carbonated system. So we wanted to explore that to understand how we can either maximize or minimize the amount of calcium ions in the silica gel itself. So I will start by talking a little bit about the reaction kinetics. How is that reaction happening? So we look at all those materials that we produced and look at how do they carbonate, how quickly they carbonate, what is the mass fraction of calcium carbonate or limestone that we are forming. And if you look at those curves, you can see that they are clearly showing two slopes, right? There is a very rather steep slope in the beginning, and then there is less steep slope at the end. And not only that, you can see that the separation of those points at the end is much closer than the initial separation of those points. Now, we take the cement grain, we expose them to CO2, we form those layers of silica, and we can use various techniques to determine how much calcium carbonate we have. So we look at those reaction stages, and we look also at the microstructure that is associated with it. And in the first stage, you can see this is a cement grain with a little speckles of material. That's a calcium carbonate that starts forming on the surfaces of this material. So the calcium carbonate forms at the solid-liquid boundary. So there's a little bit of water that we add. That water facilitates the development of carbonation process, and we start depositing those materials here. So the mechanism that we assumed was intermediate nucleation of all surfaces. And there are some thermodynamic reasons for this nucleation. And then when we go to the second stage, you can see that those initial nuclei grow into the larger particles or crystals of calcium carbonate. That's the binding phase that is present. So we have stage 1, phase boundary control, and we have stage 2, that is diffusion control. Because now when you form this barrier here, CO2 has to go through it. and it has difficulty going. Diffusion process is a slow process. We are not able to achieve more than about 50% of carbonation, which means about 50% of the grains originally present are actually not carbonating. We are working right now on trying to improve the efficiency of this process. So we did some kinetic modeling. We determined the various constants for those processes, and ultimately ended up with proposed model on nanoscale, really, of what the hydration products, or reaction products, I should say, look like. So we discovered that there are some small gel pores in this material. There is a calcium-modified silica gel, and so those are within the clusters itself. Then the clusters are getting together, and there are larger gel pores between the clusters, and dispersing that, you have those crystals of calcium carbonate that is the main binding phase. So we are interested in seeing how the presence of this silica gel modified with calcium influences the properties, and to what extent can we control how much calcium is in this gel. So that's what I will cover next. It turns out that some of those materials that we were working with produce something else. They produce amorphous calcium carbonate. So if I go back here, some of the materials produce calcite in the crystalline form, artificial limestone. But some produced amorphous calcium carbonate. We put it into the XRD machine, you don't see any peaks. You see the hump. But by other chemical methods, we can determine the calcium carbonate. So it's interesting to know, why do we produce amorphous rather than crystalline calcium carbonate, and what is the effect of the presence of this amorphous calcium carbonate on the actual behavior. So there is a different surface area that is associated with it. There's different reactivity that is associated with it. I don't have time to go into the details, but I wanted to highlight that that's one of the things that we were looking at. So based on all this, we determined the rate constants, and we determined the, and you can see that they were different for different materials. We've done some modeling, and theoretical slope that we were expecting for the stage 1 should be 1. We got somewhere between 1.2, 1.5. And theoretical slope for the second phase should be about 0.5. We got anywhere from 0.3 to 0.6. We also got the activation energies associated with the process. And you need those values for both stages if you want to develop a model for optimization of the carbonation process. How much CO2, what concentration, what temperature. You cannot move forward if you don't have this data. That data was not available for the materials that we were interested, so we determined those for all those materials that are part of this cement. Then we look at how the compositional changes associated with the difference in carbonation influence actually the degree of polymerization of the product, if you will. So I will start by highlighting what is the form of silica that is present in materials that we make the cement out of. So you can see this is tricalcium silicate, dicalcium silicate, and you see those little pyramids or tetrahedrons. That's a tetrahedron that has 4 oxygen and silica in the center, and you can see that they are separated from each other. And you can see that there is calcium ions all around. So during the carbonation process, these calcium ions get, they're leaching out, and then those tetrahedra will start combining. If you look at the other materials like rankenite, that is non-hydraulic, you can see that we have 2 of those always connected. We call this stage Q0. This is Q1 because it has one tetrahedra is attached to another. Oops. I must have pressed something wrong. Sorry about that. And then you have wollastonite. You can see that each of those is connected to 2. There's a state of Q2 that we call it. And there are different types of silicates. And when we expose this to carbonation, what happens is, in the presence of carbonate ion, which is this, we will create some different binding phases. In the hydraulic materials, we are creating calcium silica hydrate, which looks like that. So you can see that each of those pyramids is connected to 2 others, right? So that will be Q2 state. In carbonated systems, especially when you have calcium-modified silica gel, you will actually have mostly Q3 and Q4 present. It means that this tetrahedron is connected to 3 others, and this one is connected to 4 others, right? So it's a different orientation of individual molecules in the system. Physically, what happens is, depending on the degree of polymerization, you will get different products. And also, the different degree of polymerization of silica results somehow in formation of different forms of calcium carbonate. So limestone, calcite, is crystalline form and looks like that, sort of cubical crystals. But there is also veterite that is more sort of a leafy-like material, and there's aragonite that is more rod-like. This is all calcium carbonate, but it's just different morphologically. And you have amorphous CaCO3. That picture doesn't tell you anything. It looks like glass, right? And all of those form in the system that we're examining in different proportions. And the amount of either vaterite or aragonite or calcite that forms depends on the type of material that you started with. When we look at the non-hydraulic materials, gamma, C2S, C3S, and CS, C3S2 and CS, you can see that, for example, this wollastonite doesn't have any of veterite, right? It just has calcite and aragonite. But this one has a lot of veterite. So you would expect that they will behave differently, and they do. So when we combine those two and look at the ones that contain or not contain amorphous calcium silicate, what difference does it make with respect to performance? So we did some mechanical evaluation. We use nano indentation. We also use dynamic vapor sorption that allows you to determine the distribution of the pores that are present. And we did some processing of the data from nano indentation to determine what are the in situ values of things like elastic modules, for example. So we were able to use some well-established theories for deconvoluting the values of obtained from the nano indentation on all those points, and we created essentially a map of distribution of the elastic modulus. In other words, we were able to associate a given phase that formed with the given value of mechanical properties. So, for example, calcium-modified silica gel had the highest value of modulus. Calcium carbonate itself was lower, unreacted grains were lower. And the summary of that work is actually presented here. What we found out that poorly crystalline forms of calcium carbonate have lower elastic modulus compared to well-crystalline forms like calcite. Elastic moduli of calcium-modified silica gel were similar for all matrices. And this is creep modulus, and again, poorly crystalline forms of calcium carbonate had lower creep modulus compared to the well-crystalline forms. So that tells you that if you want to maximize the mechanical performance, you need to do something to either produce more of crystalline forms, or if you are maybe interested in material that is a little bit more ductile, maybe you need to produce less of those crystalline forms. we've done some evaluation of the mechanical properties. You know, all the pastes were contain about 50% of calcium carbonate, but that's the global number. What is the percentage of veterite? What is the percentage of aragonite? What is the percentage of calcite? That's what we determine, and you can see a very nice trend here. The higher amount of amorphous material, the higher the value of flexural strength, for example, right? So the phase composition has the influence on mechanical properties. We've also done many other evaluations, including durability studies, and I just wanted to finish with this to show you behavior in the environment that is rich in sulfate. You know, Western United States, they have a lot of soils that have a high concentration of sulfates in them. And if you put ordinary Portland cement, after about 9 months of exposure, that's what happens. You put this new cement in, 18 months of exposure, nothing happens. Very durable. Part of the reason for the durability is that it doesn't have any calcium hydroxide, which is a byproduct of ordinary Portland cement hydration, and that calcium hydroxide reacts with sulfates, forms gypsum. Gypsum causes the bending and the deterioration. There is no dead material here, so the material is just fine. What I wanted to do is switch gears a little bit and talk about our work on 3D printing technology, which is something that we've been working on for the last 4 years, I guess. We got a couple of grants from National Science Foundation, and we got a couple of industrial partners that are interested in working with us. So whenever I start talking about 3D printing, people say, how valuable is that? Is that for real, or is it a fad, right? And I think the answer is somewhere in between. It's new, so a lot of people start working on it, and progress is being made on a daily basis. I open, I'll get to that in a second. If you look at the sort of a life cycle of technology, and if you compare it maybe to your own life cycle, human life cycle, right? So you are being born, you are growing up, you mature, you reach the retirement age, and then you go to the nursing home or something like that, right? So where are we in that cycle with respect to the technology? We are somewhere in this red box. So, you know, initially your audience are really innovators, people who try to see whether that will work. Nobody else is interested in that. Market is obviously small, if not zero. Whatever is being produced is very high priced, right? A custom printer is expensive. You don't sell anything. But eventually, there will be some early adopters. The people who will start producing hardware, if you will, for printing, developing mixes for printing, so the market starts expanding, and that is growing. You know, we are still not at the mature stage. I say we are crawling, or maybe we are walking, baby steps, right? At this point. But this was announced yesterday, actually, October 24. And Dubai, they claim that they went into the Guinness Book of Records because they're the first one. They printed the largest 3D, or 3D printed the largest two-story building, roughly about 7,000 square foot. Came directly from the printer. So, and actually, the plan for that country, for Dubai, is that by 2030, they will have like 20% of their infrastructure printed. There are a variety of reasons why the people want to print. Shortage of the labor force, ability to be creative with shapes. You know, part of the reason that we are building what I call temporary housing here, which is wooden frame housing, is that allows for flexibility of creating a nice spaces. Right? People don't like concrete bunkers to live in. But if you can customize economically and create, you know, round shapes or whatever shapes that are more attractive, that will be a tornado safe, right? The other thing is you can use local material. You don't have to do it with cement. You can do it with clay that is activated by alkalis and print. So there is a lot of potential advantages. You can customize to the desire of the client and so forth. So I think that innovations that are happening right now are going to transform the way we are thinking about materials. You know, I've been to Switzerland about last year, about a year ago. There was the first conference on 3D printing technology applicable to concrete, and they were showing, you know, very nice structures. You can see this is all very fine detail. That wasn't actually printed. What they printed was the mold to cast it in. But even creating a mold that would be that detailed would be very difficult, right? What we are working on is a little bit more fundamental. What we are looking at is what we call changes in the internal architecture or layout of the individual filaments, you know, those ribbons of cement paste in this case that we are printing, and how the different arrangement of that can potentially influence the behavior. We are kind of inspired, or we are getting the inspiration from nature. You know, nature, for example, uses what we call the Bouligand structures that make the skeletons of various sea creatures, for example, very tough. They are all made from calcium carbonate, like cement is, right? Or hydrated concrete is, especially if you carbonate it. But you know, they are behaving very well. They are composite materials, and the arrangements of individual layers of calcium carbonate is such that it forces the propagation of the cracks in certain direction. So this is bio-inspired. So for example, if you use a mantis shrimp, it has a club here that it uses to kill the prey that he wants to eat. You know, it has this very elaborate arrangements of layers of calcium carbonate that actually make it very tough weapon in this case. So we were trying to duplicate this, you know, following this Bouligand architecture. And I hope you realize that the only way to do it is really to 3D print it, right? Because otherwise, you know, how would you make it? You know, it would be impossible. So we tried variety. You know, we were varying the gamma angle and producing multi-layer structures with various characteristics. You know, we did evaluation of some of the mechanical properties. So we were looking at, you know, what we call the lamellar structure that you can see that's printed. We are also looking at the Bouligand architecture, so you can see that, you know, we were varying the orientation of the individual filaments. Some of this will work. Let's see. So you can see we are printing that, and you know, the printer is capable typically of keeping a very good shape. What's happening, and we produce a variety of those elements, beams and cubes, and we tested them, looking at the mode of failure. And if you look at the load versus displacement, you know, the gray one here is the cast element, and then you have this Bouligand structure with various degrees of orientations of filaments and various percentages of infilling. So some were, you know, some were essentially solid, some were not so solid, right? And, oops. And if you look at some of the mechanical characteristics, for example, work of failure, or even the ductility, if you look at the area under the scales, you can see that orientation of those filaments matters. And you can see that if we have, for example, this structure that has 40% less material, it actually behaves almost like the solid materials that we cast, right? And the other thing was, this is a look at the modulus of rupture. Modulus of rupture, and you can see that we didn't sacrifice the strength very much by not infilling it completely, just by keeping the orientation that was different. Now, when we summarize all of this and look at some theoretical work, prediction of modulus of rupture as a function of the relative density. So those are two different models that predicted how the material should perform. And you can see that many of the structures that we created were actually above those lines, right? Which means that we actually achieved the higher toughness than predicted in this particular situation. So we outperformed the strength compared to hydrated cement paste counterparts that were solidly cast. We were interested in exploring what is actually happening, why we have this increase in toughness. So we did some CT scanning in various configurations. So you can see, I'll be using this nomenclature, like XY plane is I am loading perpendicular to the XY axis, right? And XY plane here, or XY plane here, or XZ plane here. We're looking at the way the material was failing. So this is a stress-strain response, and again, you can see that in some cases, like this red one, when it's loaded in the XZ plane, it has almost the same value of stress. It has actually a greater ductility than the cast material, right? But if I load the same material in other direction, it's not going to behave as well. So from an engineering point of view, you would have to decide how are you going to use the material that you print. And if you want to take advantage of this increased ductility, you need to orient the element accordingly in your structure. So, when the XZ plane, that's the way we are looking at it, and that produces that curve. So if we are loading along the filaments, as we were printing, that has the best behavior. If we load in the direction perpendicular to the filament, or in the direction perpendicular from the other side, the response is not that favorable. If you look at the mode of failure, you can see that for the cast element, so this is the regular cast element, there is no distinct crack pattern. What we get is a failure that looks like a typical shear cone. Normally, there'll be a failure due to the tensile stresses, but because of the restrictions of the platens, we get this confinement. And if you look at the Morse circle, that actually produces the shear cone type of a stress. And if you look at, I don't know how well you can see that, but this is another one that is lamellar tested in the other direction, and you can see that there is a crack pattern that is interfacial. If you look at this movie that is playing, notice that the crack doesn't go perpendicular. It goes partially along the what would be a weak interface between the filaments, and then kind of spreads in the direction that is diverted. All this meandering of the cracks consumes the energy. That increases your toughness. That increases the ductility of the problem. So we published that, and we get actually contacted by a company from San Francisco that are interested in looking to what extent that kind of arrangements may help with mitigating the damage due to the earthquake. Granted, this is not reinforced or anything, but the fact that the material itself can be actually more ductile than the cast material in a sense that it consumes more energy was of interest to them. And this is testing in another direction. And again, if you look at the mode of failure, you can see that again the damage sort of tends to be along the weak zones. Weak zones are the zones between the filaments. We actually are working right now on trying to reinforce those weak zones by using short fibers that will be helping bridging some of those gaps. And you can extrude the fibers at the same time as you're extruding the filaments. You can use another nozzle to put the fibers on the deposited layer of filament. So that technique kind of allows you to modify, allows you to be innovative, I think. And we have a lot of undergraduate students. We show that in our undergraduate courses, and they requested that we actually create the one module, one credit-hour module where they can play with some of those concepts. So we taught that course last semester. Was very well subscribed. And students were printing all kinds of interesting stuff. So that's what makes the topic attractive to the students. And say, oh, I didn't know you can do that in concrete. So that's something that is attractive to younger generation that likes to play with the computers and some innovative things. This is tested in another one, in another arrangement. You have a different crack pattern. That I don't want to dwell on that because I am getting close to my allotted time. So I wanted to finish by summarizing what we learned so far from this. Damage mechanism that exists in those 3D printed elements is different than the damage mechanism that is present in the cast element. And particularly the architecture, internal architecture, influences the way the materials fail because we are altering the damage mechanisms. And not surprisingly, you have micro-cracking at the interfaces, but rather than viewing it as a bad thing, you have a weak interface, by changing the orientation of those weak planes, we're taking advantage of it, try to redistribute the cracks throughout the microstructure. So if we do that, if we redistribute the crack, we'll have a higher Walker failure compared to the cast counterparts or specimens that were just created using the regular casting process. This is all I wanted to share with you. Thank you very much for your attention, and I think we may have a few minutes for questions. Okay? Thank you.
I'll borrow your microphone. So time for questions, and I'll have to bring the microphone to you. All right, Bernard. Thanks for coming.
Thank you. Thank you very much. Yes. Yeah, very interesting perspective on these A lights, B lights, and the other components. I wanted to ask, when we now use Pozzolanic substitution, how do these influence the Pozzolanic reaction?
I have to get the microphone to you. Hold on. Sorry.
So I'm not sure if I understand your question. You mean, how would Pozzolanic substitutions influence a Pozzolanic reaction?
No. How will Pozzolanic substitution, what parts do these enhancements, C3S, C2S, CS, how do they now play into the Pozzolanic reaction?
Okay, so the Pozzolanic materials that we use, fly ash, slag, silica fume, metakaolin, and so forth, right? They are called Pozzolanic materials because they do react with calcium hydroxide that is a byproduct of hydration of tricalcium and dicalcium silicate. So the regular Portland cement, it is producing a lot of calcium hydroxide, and if we substitute part of the Portland cement with those materials, we also produce quite economical I will call it green cement, right? Because first of all, you use less Portland cement because you substituted part of it with, in case of slag, maybe up to 50%, or high volume fly ash, 50%, right? But it's a different product than the one I'm talking about here, which is a carbonation product, because it's still a hydraulic reaction that is happening. And the Pozzolanic reaction is a hydraulic reaction that produces the same product, which is calcium silica hydrate, as the regular Portland cement does. What I was talking about here is the material that is non-hydraulic. And that means that it will, if you put it in water, it will not hydrate. If you add fly ash to that, nothing will happen, because there is nothing for the fly ash to react with. The only thing that you could do, if you wanted to utilize fly ashes in the system that is non-hydraulic, you have to activate it and essentially produce geopolymer. Okay, so that would be different material. Okay.
Any other questions?
Yeah.
Okay. Yeah, thank you very much for your talk. I believe the title was Innovations in Concrete, and your last topic, for example, this 3D printing, it seems that you're printing with cement. So where does the concrete come in your 3D printed cement?
Okay, so the only reason we don't have a concrete is because we don't have a printer capable of printing the concrete. We actually have a company right now that is buying as a printer based on this work, because they want to duplicate these Bouligand structures in the elements that will be used for construction of the towers for wind turbines. Some of those towers are very big. Diameter at the bottom may be up to 8 meters. They are too big to be transported on the highway system because of the clearance issues, so they want to 3D print them. And they think they can 3D print them with this architecture, taking advantage of architecture that will make it lighter, and the pre-stressing ducts that will be necessary to put those segments together to create, 130 meters or 130 feet tall tower that will be a little bit better spaced based on some modeling that was done. So printing of concrete is not easy, and majority of people who print with concrete, the maximum size of the aggregate they use is about 3/8 of an inch. So I'll call it a coarse mortar. Ultimately, if the technology is developed where you can have a matrix, meaning paste, capable of holding larger particles of aggregate under pressure in the nozzle, it will be possible to print with concrete. Right now, we don't have admixture system that will actually allow for that. So the larger the aggregate, the easier it is to separate the aggregate from the stream of flowing paste. And several companies, including Sika, one of the largest manufacturers of admixtures, are working on, they form a division specifically looking at the viscosity modifiers that can be useful for 3D printing. So the fact that there are companies that are producing the printers, you can actually go and buy a printer right now. 3 printers. You can buy one in Italy, you can buy one in Holland, and you can buy one in Denmark. Well, there was actually an activity in Minnesota. I don't know if you've ever seen a printed castle. That was done here in Minnesota. We are talking to this guy as well about potentially working with us on developing a sort of scaled-down version of the printer. But if we have a technology on the ink side, concrete side, the manufacturers of hardware that will allow for printing are there. Just need to work a little bit on materials. Okay.
We have time for one more question, if there is one. No? Okay, let's thank our speaker one more time.